stuff. So what I'll do is that I'll peel the onion a little bit and kind of show you like some of the technology foundations we have in our system. Just to summarize what Rex said a little bit was that Datrium is about offering 3 solutions packaged into one platform. And the goal is to actually simplify the customer's life and to basically make it convenient for the customer to do this. So we aspire to provide the best capabilities for the applications running in our system in each of these areas. That's the goal. So why did we come to this conclusion? So if you look at the layer just below the hypervisor, the app orchestration layer, it's all about data management. So you start your day with running your applications. You start your day with, I think, doing backups. Then you end up doing DR planning. So all of these things take multiple platforms and multiple vendors to kind of work on this. So we found that actually is challenging for a lot of people. So how can we simplify this? The world is trying to want a convenient system. So we kind of try to look at that. Then we thought of this problem as part of the company. Then the other question is, OK, is there a common foundation, technology foundations we can apply to this? We made a giant list of all the features customers would like us to go build. I'll show that list in a minute. It was a giant list. It was a huge list, and it's sometimes a little daunting for a startup to look at that. But since you're a startup company, you can have a clean page. You can look at all that stuff. So what we concluded was that there are 3 things. If we build these 3 things, we can go and solve these problems. So these are the 3 things we found to be the key foundations for us, at least, to help us build anything on top of this. So one was a log-structured file system. The other one was global dedupe, and the third one was a backup catalog. I'll talk about them in a little detail. But I want to talk about how we came to the conclusion of these 3 first. So here's a list of problems. I mean, I can't see the background, but there's a huge list of issues. But we found that if you solve these 5, we are good. Like, we can solve everything. So basically, sometimes you get that, if you solve these, everything else comes for a free ride kind of thing. So let me explain each one of these a little bit. So SSDs are good for random reads, clearly. But if you put the SSDs over a wire, you have the Little's Law problem. That means latency, fundamental latency issues if you put over the wire. Then the random write problem. So everybody knows that hard drives are really bad at random writes. But SSDs also not very good at random writes. If you do sustained random writes with SSDs, at least the commodity SSDs, they don't really work well. The most storage systems have been built to deal with fixed size blocks. But compression messes with that. It makes everything variable sized. Your 4K block becomes 2.78. It's actually a pretty challenging problem to solve in storage. Then there is the global dedupe. When I say global dedupe, what I mean is that there's dedupe on both sides, and you can transfer the data, knowing that there's dedupe on both sides. You optimize for that. And third one is that we wanted to build something which has millions of objects and be able to search in the catalog and search it fast. So these are the 5 problems. So let me walk you through how we came to the conclusions. So foundation 1, a log-structured file system. So there is a paper by Mendel and Ousterhout from UC Berkeley in 1992. Last year, they got a 25-year award, Test of Time award, for actually being a good paper, and everybody still uses it. It was kind of left aside for a little while. I think it started becoming popular in the last decade a little bit. So also, Mendel happens to be the founder of VMware later on, and he also is an investor in Datrium. Coincidence? So what's the main theory? The main thesis in the paper was that you can convert a random write, package into a sequential log, and write it to disk. Disks are really good at sequential writes, like SSDs are also. But you can't get any better than this. So if you can convert this random writes into sequential writes in the disk, your performance problems go away. Then there's some challenges. Some of the challenges, I think, were solved in the paper, but a lot of the challenges were left for the reader to go solve. So what's our enhancement to this? So that's the initial idea, which is great idea. We took that. So we want to stand on the giants. We have enhanced it to do distributed LFS file system design with a petabyte scale-out object store. We built inline compression with it. And we have inline erasure coding. And ultimately, we have done large-scale we solved large-scale problems in the system. So you may be wondering how this works. So I'll just give you a quick, it's a very simplified overview. If you have questions, I'm happy to answer. I wanted to show a quick simplified overview of the whole thing. It's not the the full picture of how the I/O path works, but I want to just show you like how a little bit of how the I/O path works. So there is a VM. So there's two pieces in this. Our software stack, which runs in the compute nodes, which is our software stack, and this is just data nodes, which has just bunch of drives across them. So there's a VM, and VM has incoming writes, random writes coming into it. So we do log the random writes first. We compress it and write to NVRAM. I didn't show the picture here, but since the question came up before, I'm going to talk about it. So we compress it and write to, we acknowledge it back. There's an NVRAM piece on the data nodes. We write to it, and then we respond back right away. Because you cannot wait, because you want fast responsing. So you can't get any better than writing to NVRAM in some place and coming back from it. So in the background, we try to collect the data, and we try to dedupe it by computing crypto hashes. We try to dedupe it. And if the dedupe is not matching anything, we will compress the data.
Sazzala,
Yes.
the data for a write is not acknowledged to the host until it's actually persisted on the back end?
Yes.
Correct. I thought you just said that it acknowledges back after it's hit the NVRAM.
Yes. The NVRAM is not in the host. It's in the data nodes.
Right. Oh, I see. Right. OK.
These are all stateless. You can kill every host you want, and then data is always in the data node. Sorry, question?
No, it's fine.
OK. So you compress these blocks, and you pack them into this something called a container. Container is a popular word. I've noticed everybody uses the word container, but for us, the container means this 8 megabyte container. So you pack it in the background. Because you're able to pack it, it doesn't matter what the variable size is. It could be 1.7. You can compress as you want. Once you have a full container, you take that container and you make it into erasure-coded blocks, into 1 megabyte pieces, into P and Q, and then you stripe that across all the data, all the disks, or whatever number of disks you want to stripe across. This is across the data nodes. The data nodes are quite simple. They actually just have a JBOD, some NVRAM. They have some control logic, but it's mostly just very, very simple boxes.
So is a container split across multiple data nodes potentially?
Yeah. Think of the data nodes as just storing these 1 megabyte blocks. They don't know much about the container. They know something about, but not much. So each of these data nodes projects. So each of the drives in them are addressable by so it's like a network pool of drives.
Right.
To move the drives around doesn't matter. It's a network pool of drives. All these hosts directly talk to the drives in some sense.
So the metadata that would map a virtual machine's file, for instance, to containers and so on, that has to be on the back end.
Yeah, it's always in the back end too. So it's always, the truth is always here. So all the data is represented as crypto hashes. It's a giant dedupe pool. It's a content address, basically. It's a content address addressable system. Yes, we have the container to store the data, but ultimately the system is basically a giant pool of content addressable store. So it's all crypto hash and global dedupe. So you have a bunch of data, with crypto hashes, like let's say 4K blocks. They are meaningless by themselves. They're just stateless. Each 4K block has a crypto hash. You move it around, doesn't matter. It's stateless by itself. What we then do is that each VM and each VM snapshot is represented by a list of crypto hashes. That is where the representation of the data really is. If you have a VM with 100 gigs, whatever, it has a list of crypto hashes which represent what that VM really means. So we take that container, erasure coding it, and then anything is good at large writes. It's pretty good performance. Performance is very stable. At 1 megabyte writes to these devices, you can do the math on a piece of paper and see what performance you're going to get before even writing a single line of code in the system. That's a very simplified overview. I think I want to go too deep into it. So the picture I'll draw a little differently from what Rex had it. So this is data nodes. They come together to form this capacity pool. And our software runs on each of the compute nodes. They project together one giant NFS data store as a global namespace.
I do have a question.
Yeah.
How big is the NVRAM in those nodes?
It's about 8 gigabytes. We don't need too much because you need enough to acknowledge the data back, enough to wait for the container to be formed and to write to the disks, and then you can delete the NVRAM data.
Is it always watermark based when you flush?
Sorry?
Is it watermark based when you flush? Timed? How do you flush it? How do you know when?
Yeah, so you flush it. You don't flush that way. You delete it. So the way. So let me go back to the picture.
Delete it.
So you write to the NVRAM. It's a little bit of NVRAM. In the background, you're collecting this. So once you get 8 megabytes of data, this data goes to the disk. Once this goes to the disk, that data in the NVRAM is no use anymore.
Right.
You can delete that.
I call that flushing. Fine.
You can, yeah. Flushing means that you're actually doing work to actually write the data there. That is not what we are doing. We're actually deleting this thing. We don't need it anymore.
Okay. Is it also in RAM? You have it in NVRAM and RAM, and you're just working on the RAM, and then when you're done with it, you just put it in?
Yeah.
Okay, same as NetApp. Okay, fine.
Yeah, it's kind of, same theory. I agree with you.
There's only so many ways you can do it.
Right.
And the NVRAM is mirrored across all the data nodes?
Across two. Okay, we have at least two NVRAM copies in the system. By the way, when we write the data out here, we also write this data locally into the local SSD cache. It's also deduped locally, so you can just write it there. So just so you have a copy of it. It's the most active data. It just came in, so you better keep it on the local cache.
Local cache on the node or in this?
On the node.
On the node. Thank you.
So because we have LFS here, we also have similar technology to use LFS in the local SSD. So once you have LFS, if you do large writes, even any commodity SSD will work great. It'll have long wait out time. So basically, we don't need high performance. We don't need this expensive SSDs on the local caches. We make any commodity SSD look like really amazing performance, and not wear it out. Also, because we do compression dedupe, we actually studied recently in our customer base. We get data back from our customer base. We found that our average dedupe and compression ratio is about 4.4. So if you do that math, so if you get 2 terabytes of SSDs on each of the local hosts, it's about 10 terabytes of cache on each. 10 terabytes is no longer a cache. Everything is there, so you get no cache misses. So that solves the random read problem. So once you have a big cache, there's no reads going anywhere. Your performance is really amazing. You will notice the difference. It's like laptop-like experience. And what is the capacity pool? They work together to form a giant, durable capacity pool. We can use commodity hard drives. And we also have a version which uses SSDs if in case you want it. What we get is that we solve the random write problem, which is pretty part of our random write problem. No, we can take on any random write problem because it's nothing for us. We convert it all into sequential writes. We actually have benchmarks on pure random writes, which Rex did not show. It's like it's really amazing. And finally, we solve the variable size blocks problem. So I think we've solved these two problems. The next problem, well, actually, before I go there, what we found is that by solving this by using a log-based file system, we get high performance, full stripe writes. And we also do not do read modify writes. Like RAID has a read modify write problem. We have no read modify writes ever. We never do overwrites, so we have no corruption problems like that. We always write in new places. And it's very cost efficient because you can use cheaper logs. And see, ultimately, we have dedupe in a system. We need a way to keep track of the dedupe index. And there's something called LSM trees. It stands for log structured merge trees. It was made popular again by Google. People started using it. It's a way to use a log to build a tree on top of it. So it's very highly efficient for writing random keys into the database. It's a topic by itself. I could talk about it for 2 hours if you want, but I think Craig is looking at me right now.
Rachel will like it.
And because we do never write in the same place, we can do snapshots very easily. We can do a million snapshots. And ultimately, we started in 2012 as a company. The advantage is that Amazon already was there in 2006. You have to prepare your mind to like, OK, I got to make this work in the cloud. And we found that S3 is the most efficient way, most cost-efficient way of using something. And if you're going to move something to workload to the cloud. And S3 is very weird. S3 has a really weird architecture that if you do random writes to it, it doesn't like it. If you do partial override, it doesn't like it. So it wants a full object write, sequential write. So that's what we write. Containers is a perfect match for us. So when we built our cloud DVX, we took our software and we ran it in the cloud. So here we have wide striped objects, the containers. Here a container maps to an S3 object. It works perfectly. We don't have to change too much of our file system to actually make this work in the cloud. So it actually works quite well with all the same feature sets, same everything. So foundation number 2 is global dedupe. The way we do global dedupe, in the sense, the global dedupe, again, what it means is that there's dedupe on both sides, and you're able to do WAN optimization and not send over what's you only send over what's missing on both sides. We use crypto hashes. Every VM and every VM snapshot is represented by a list of crypto hashes. The question then is, how do you so if you're going to do a cloud, if you're going to do DR to the cloud, if you're going to move data around a bunch of times, the question we ask is, how do you know that fundamentally you actually have moved the data correctly on both sides? I mean, what is the probability that that you've missed a bug or something, software corruption? So what we've decided to do is that we'll have bugs for sure. First acknowledge that fact, and then if you represent a VM or a VM snapshot with a list of crypto hashes, it's like blockchain. If you move the data from here to there, you can independently verify on both sides that I got the data I believe I should be getting. No matter what the bugs in between are. If there's bugs, there's something will mismatch, it'll fail. When you fail, you can go take remedy action. So that's what blockchain is about, right? I mean, how do you get guarantees in the system about moving data in the cloud? So this is something we're concerned about, is that if you're going to move data back and forth, which we want to, you need to be correctly, you need to make sure that actually works. So we've done a lot of stuff like this. So to actually get data integrity in a system. So dedupe people think is only for data efficiency. Actually, we use it for data integrity.
Can I ask about your hashing algorithm?
It's a variant of SHA-1, but it's a little secret. Partly because we don't want people to like produce something and say, okay, it's matched.
Secret by definition.
The other thing I said about the Snap Store was that we have built a catalog for searching. It's very fast. You can store millions of objects. And we can do VM policies at VM level granularity. And you can do operations of recovery. So we call that a catalog. We call it search catalog or backup catalog. Those are the three foundations we have built in our system, which enables us to build everything else we feel in our system.